This video will go over the practice question 2, hydrogen spectrum, from the 2007 NZQA exam. So, in our first question here, we're told that the electron in the hydrogen atom emits or absorbs electromagnetic radiation when it moves between different energy levels. The visible part of the spectrum emitted by hydrogen can be seen in the laboratory by applying a high voltage to a hydrogen discharge tube. The diagram below represents some of the electron energy levels in the hydrogen atom. Alright, question A asks, to which energy level does the electron drop when it emits visible light? We know that that's energy level 2. Oops, let's just get our pen back. So that's energy level 2. So that's the Balmer series. That's the series that we observed in class. The absorption spectrum for hydrogen gas consists of a series of dark lines within the full spectrum of colors. Explain clearly how the dark line in the red part of the spectrum is produced. Okay, so to answer this question, what I'm going to do is give a short answer. So we can start with the idea that when white light is shone through hydrogen gas, those photons which have energy corresponding to the difference in the energy levels of the electron will be absorbed. The red line that's missing is due to photons being absorbed by electrons in energy level n equals 2, causing the electron to jump to energy level 3. So those are absorbed. Because these are absorbed, they are not present in light emerging from the gas. Okay. Question C says, calculate the frequency of the photon produced when an electron drops from the second excited state n equals 3 to the ground state n equals 1. So the frequency of that photon, there are two ways that we can do it. We can either work out the energy difference using the equation for Bohr's energy levels, or we can use the Rydberg equation. I'm going to use the energy level method. So delta E electron is equal to negative HCr times 1 over 1 squared minus 1 over 3 squared. So that's equal to 6.63 times 10 to the negative 34 times 3 times 10 to the 8, which is the speed of light, times 1.097 times 10 to the 7 times 1 over 1 minus 1 over 9, which gives us, so that's 6.63 times 10 to the negative 34 times 3 times 10 to the 8 times 1.097 times 10 to the 7 times 1 minus 1 over 9. I left out a minus sign there. So that's, let's get that in standard form. It is 1.939 times 10 to the negative 18 joules. And in fact that's negative. So E photon is going to be 1.939 times 10 to the negative 18 joules. But we also know that E photon is HF. So F is equal to 1.939 times 10 to the negative 18 divided by 6.63 times 10 to the negative 34. Which gives us 2.93 times 10 to the negative 15 equals 2.93 times 10 to the negative 15 hertz. Okay. The alternative method you could have used is just to work out the wavelength, but it's really the same process because this equation here was derived from that other equation. Okay, an electron in energy level 4 jumps to a higher energy level and then drops down to the ground state, releasing a photon of frequency 3.2 times 10 to the 15 hertz. Calculate the frequency of the photon required for the first jump. So here it's convenient to draw a little energy level diagram where we have these states. Oops. So we have some energy level there, we have an energy level here, and we have the ground state. So the final step here is this jump there, and that produced a photon of frequency 3.2 times 10 to the 15. So we can easily figure out what the energy difference is between those. We don't know what state that is. We know that's the fourth state, and we know that's the first state. The first jump is the jump up to there. So we need to use this information to figure that out. So if we can just work out what that amount of energy is, let's call it 4.1, and then we'll subtract this energy from the energy of that photon. That should give us the difference between these two energy levels. And once we know the difference between those, then we know how much energy the photon must have had that came in to cause that jump up. Okay, so let's do that. So E photon is equal to E from question mark to 1, which is equal to HF, which is 6.63 times 10 to the negative 34 times 3.2 times 10 to the 15, which is equal to times 3.2 times 10 to the 15 gives us 2.1216 times 10 to the negative 18 joules. Okay, and E from 4 to 1 is equal to HCR times 1 over 1 minus 1 over 4 squared, which is equal to, so H 6.63 times C 3 times 10 to the 8 times R, which is 1.097 times 10 to the 7. Oops, I forgot to do that. Let's try that again. I forgot to put in Planck's constant. 6.63 times 10 to the 34 negative times 3 times 10 to the 8 times 1.097 times 10 to the 7 times 1 minus 1 over 4 squared is 16. and that gives us, let's give us in scientific notation, 2.05 times 10 to the negative 18, 2.04556, let's say, equals 2.04556 times 10 to the negative 18 joules. So we can see that this one is smaller than that one, which makes sense because this jump here should be smaller than that jump there. Okay, so now delta E from 4 to question mark must be the difference in those two. So that's 2.1216 times 10 to the negative 18 minus 2.04556 times 10 to the negative 18, which gives us, what were they now? 2.1216 times 10 to the negative 18 minus, and what was that? 2.04556. 2.04556 times 10 to the negative 18 is, that seems outrageously small. Oh, I did times, not minus. Let's try that again. Let's check those numbers once more. 2.1216 minus 2.04556 times 10 to the negative 18 gives us, in scientific notation, 7.604 times 10 to the negative 20. Okay, so it's quite a small number, that's joules. And I need another line of working here, so the frequency is just going to be that, E over H, which will give us, so we want to divide this by H, that's 6.63 times 10 to the negative 34, and it gives us 1.15 times 10 to the 14.